Greetings. I'd like to do a lesson on congruent polygons. First of all, we're going to look at a definition here. We need to have at least two of them so that we can compare them. They are congruent if and only if their corresponding parts are congruent. So we're going to look at the parts, compare the parts to determine the whole. So let's start out with triangles. So I'll start out with triangle XYZ here. And then I will also have triangle MNP. Now, the question is, are these congruent polygons? Well, we need to look at the parts because their corresponding parts have to be congruent. So when we look into these polygons, we need to, first of all, let's look at the angles. I want that since X and M are corresponding, they are in the same corner of the triangle when it's orientated this way. We want to see that this angle and this angle are congruent. We also want to see that this angle and this angle, being corresponding, are going to be congruent to each other, but not necessarily to the first angle that we looked at. And then finally, the other angle we have here, we want to be congruent to that. So now we have all of our angles congruent. Is that enough? It's actually not enough to say that we have congruent. We also need sides in here as well. So we need to look at this side, XY, and it should be congruent to the corresponding side MN in my other triangle. Furthermore, XZ should be corresponding to this one and congruent. And lastly, YZ and NP should be corresponding congruent as well. Once we've identified that I have my corresponding parts being congruent, we know that these are in fact congruent polygons. In this case, they're triangles. I want to also talk about some notation. When we look at triangle X, Y, Z, when I write this symbolically, notice I put my triangle symbol and then I put the vertices. I started in the lower left corner and went around clockwise. When I go to make a notation about this triangle, being that I want to establish that I'm going to make a statement about it being congruent to the first one, I want to go through and write the vertices in the same order. So I'm starting with my triangle symbol. I'm going to start in this corner and I'm going to rotate clockwise. M, N, P. Then once I have these notationally written this way, I can put the congruent symbol in between here, and so I have a valid statement. If I had not put the angles of the second polygon in the same order as the angles of the first polygon, it would look like a different angle, say X and possibly N, were corresponding congruent parts, and that's not what we've identified here. So we want to go in the same order so that when we write them down, the corresponding vertices are in the same order with the other triangle. So this is a notationally important thing to have established. For a short time, we will focus on looking at a theorem that just looks at corresponding angles. We have the Third Angles Theorem here, which tells us that if we have two angles of one triangle congruent to two angles of a second triangle, then third angles are congruent. Given this theorem and these two diagrams, again, I'm using X, Y, Z, M, N, P. I'm going to use these as my given triangles. I'm going to put in my other given that we know that we have corresponding angles for two of those angles. We are going to prove that the third angles are going to be congruent as well. So we'll just say that X and M are one of the pairs of angles that we know, and let's say Y and N are the other pair of angles that we know. We want to prove that Z and P are congruent. I'm going to make a little note of that. All right, we're proving this. So we are given these two triangles. We are also given that X and M are congruent to each other. Angle X congruent to angle M. And we're also given that angle Y is congruent to angle N. All right, so those are all givens, those items. All right. The first thing that I want to do is I'm going to make a statement that X plus Y plus Z equals 180 degrees. That is our triangle angles sum theorem. So angle X plus angle Y plus angle Z is 180 degrees. And I'm going to do the same thing over here, that M plus N plus P is 180 degrees. All right, so we have our givens, and both of these come to us by way of the triangle angles sum theorem. Now, since I have that this sum is equal to 180 degrees and this sum is equal to 180 degrees, by transitivity, this sum and this sum are going to be equal to each other, so that's what I'm going to do next. Angle X plus angle Y plus angle Z is equal to angle M plus angle N plus angle P. Okay, now I'm going to do some substitutions. We have X congruent to M, Y congruent to N. So over here, I'm going to take my X and Y out and put in M and N by substitution. So I have angle M plus angle N plus angle Z is equal to angle M plus angle N plus angle P. And this is substitution. And now I'm going to subtract the M and the N that is in common on both sides. And that will leave me with angle Z is equal to angle P. And that was subtraction. And I need a statement about congruence. I have equals, so I can translate this into a congruent statement by the definition of congruence. And at that point, we are done with this proof. I'm going to look at one more proof that deals with both corresponding congruent sides and corresponding congruent angles. We have this diagram over to the side and several givens, and we want to prove that the two triangles are congruent triangles. So we have that RT and TU are congruent sides, RW and WU are congruent sides, angle R and angle U are congruent angles, and this angle down here in the corner by W, which is TWR, and TWU are corresponding congruent angles. So this is basically a reflection across here. So it seems reasonable that these are congruent. So we just want to run through getting those details together and proving that. So I like to start my geometry proofs with my givens. It's nice to start with the freebies. So I'm just going to list those up here. Okay, and we have these givens. Immediately we can say that these two angles up here where T is, which is RTW and UTW, are going to be corresponding congruent angles because we already knew that these two angles are corresponding congruent to these two angles. These are triangles, and so the third angles theorem applies here. So angle RTW congruent to angle W or UTW, and that is third angles theorem. All right. One last thing that we need to know, let me mark this up here in our diagram. We need to know that the base of this triangle on the left, which is base TW, has a corresponding congruent side to the base of this triangle, which is on the right, which has a base of TW. Well, if you realize I just repeated that TW is the base of each triangle, so we need to make a statement about TW being congruent to TW. This is where the reflexive property comes in, and if you've had that introduced to you in an algebra class, it may seem like a kind of ridiculous thing to have a property of, to say something like 5 is equal to 5. Reflexive property. So it seems kind of obvious there, but when we have geometry proofs like this where we're sharing a side, it's important to have that statement down there, and that's by the reflexive property. So I feel that we see a lot more realistic feel and use to the reflexive property in proofs like this. So this is reflexive property. And so now that we've shown that all the corresponding congruent parts are congruent, then by the definition of congruent polygons, we have that our item that we were supposed to prove is proven at this point. Triangle RWT is congruent to triangle UWT. This is definition of congruent polygons. Another abbreviation you might see sometimes, especially with triangles, you can see corresponding parts of congruent triangles are congruent. That's oftentimes an abbreviation that shows up. So this is corresponding parts of congruent triangles are congruent. That's basically saying that we're using the definition of congruent polygons with triangles. I've also seen an alternate version of this where the T is replaced with an F, so you have CPCFC. And what this is trying to indicate is that corresponding parts of congruent figures are congruent. So they're using figures as a generic instead of polygons there. So you might need a slightly different definition there. If we don't specifically have polygons there, we might generically call them figures and be using a different definition. But these are common abbreviations that you could see show up in texts, whether you find that in a book or possibly online. So that's what those abbreviations mean. Those could possibly be a replacement as a reason here instead of definition of congruent polygons. At this point, we've proven what we were supposed to prove, so we are done. Hopefully this gives you enough information where you're going to be able to use corresponding congruent parts to get proofs for congruent polygons, or start with a set of congruent polygons and know that you have corresponding congruent parts. And as in this proof here, we've used that as kind of our final condition. Cheerful calculations.